Hello! In this video, we are going to prove the following theorem. Let a be an integer, and s is a subset of the integers greater than or equal to a. Suppose a is an element of s, and for all integers n greater than or equal to a. If n is an element of s, then n plus 1 is an element of s. Then s is equal to the set of integers greater than or equal to a. So this is essentially the principle of mathematical induction for any starting integer. And at this point, we have proven the principle of mathematical induction for positive integers, which is as follows. Let s be a subset of the positive integers. Suppose 1 is an element of s, and for all positive integers n, if n is an element of s, then n plus 1 is an element of s. Then s is equal to the set of positive integers. Now, instead, I'm going to call this set T. Okay, so now let's get into proving this theorem. Now, to start out the proof, we are first going to consider the following set. We consider the set of positive integers n with the property that n plus a minus 1 is an element of s. And the motivation for this is we expect s to be equal to the set of integers greater than or equal to a. Well, if we translate the elements of s like this, then we expect this set to be equal to the set of positive integers. And so we are going to show that this set is equal to the set of positive integers by applying the principle of mathematical induction for the positive integers. Now, by definition of our set T, we see immediately that T is a subset of the positive integers. So all we have to do is verify these two conditions. Let's first verify that 1 is an element of T. For 1 to be an element of T, we need 1 to be a positive integer, and we need 1 plus a minus 1 to be an element of s. Now certainly, we know that 1 is a positive integer, so all that's left to show is that 1 plus a minus 1 is an element of s. Now, we know that 1 plus a minus 1 simplifies down to a. And by the first thing that we're given, we know that a is an element of s. So since these guys are equal, we can replace a here with 1 plus a minus 1. So we have 1 plus a minus 1 is an element of s. And that is what we wanted to show. So this tells us 1 satisfies all the requirements to be an element of T. And therefore, 1 is an element of T. So this verifies the first condition. Now we want to verify the second condition. To verify the second condition, let's give ourselves an arbitrary positive integer n, and suppose n is an element of T. From here, the whole goal is to show n plus 1 is an element of T. Now, since n is an element of T, well, then that tells us that n is a positive integer, and n plus a minus 1 is an element of s. And let's note that s is a subset of the integers greater than or equal to a. So then, let's go to the second statement that we are given. This statement works for all integers greater than or equal to a. So in particular, it must work for n plus a minus 1. So taking n to be n plus a minus 1, we have if n plus a minus 1 is an element of s, then n plus a minus 1 plus 1 is an element of s. Well, we know that n plus a minus 1 is an element of s. That's what we have here. So we can conclude that n plus a minus 1 plus 1 is an element of s. Now, of course, we can move the plus 1 to the right of the n. So since these guys are equal, we can replace this guy with this guy. So we have that n plus 1 plus a minus 1 is an element of s. And now, this tells us that n plus 1 satisfies all the requirements to be an element of T. Because if we take n to be n plus 1, well, certainly, we know that n plus 1 is a positive integer. Because since n is a positive integer, well, n plus 1 is bigger than n, so n plus 1 must be a positive integer. But also, we know that n plus 1 plus a minus 1 is an element of S. That's what we have here. So that's true as well. So as you can see, n plus 1 satisfies all the requirements to be an element of T. So n plus 1 is an element of T. And so we have shown if n is any positive integer. Well then, if n is an element of T, then n plus 1 is an element of T. So we have verified the second condition. And so, by the principle of mathematical induction for the positive integers, we can conclude that T is equal to the set of positive integers. But remember, the whole goal has been to show that S is equal to the set of integers greater than or equal to A. And to prove that, well, we know that S is a subset of the integers greater than or equal to A. So all that's left to show is that the integers greater than or equal to A is a subset of S. Because those two inclusions imply that the two sets are equal. So to prove that the integers greater than or equal to A is a subset of S, let's give ourselves an arbitrary integer greater than or equal to A. I'll call it n. Then we have n is greater than or equal to A. So if we take this inequality and subtract a minus 1 on both sides, we get this. But really, a minus 1 is equal to 1. So we have n minus a minus 1 is greater than or equal to 1. Now certainly, n minus a minus 1 is an integer. So n minus a minus 1 is an integer greater than or equal to 1. And that tells us n minus a minus 1 is a positive integer. But the set of positive integers is equal to the set T. So this tells us that n minus a minus 1 is an element of T. And since n minus a minus 1 is an element of T, what does that mean? Well, if we take n to be n minus a minus 1, it means we have n minus a minus 1 as a positive integer, and n minus a minus 1 plus a minus 1 is an element of S. But the a minus 1's cancel out, and this is just equal to n. So we have n is an element of S. So this shows if n is any integer greater than or equal to a, then n is an element of S. And that tells us that the set of integers greater than or equal to a is a subset of S. And so, since S is a subset of the integers greater than or equal to a, and the integers greater than or equal to a is a subset of S, that tells us S is equal to the set of integers greater than or equal to a. And so this completes the proof. And so yeah, that's pretty much it for this video.